In this lecture, we're going to focus on the idea of the inverse of a given function. As an example of this concept, consider the function f, which assigns to each student at a university his or her ID number. So the domain A of the function f is the list of all full names of students, and the range B is a set of natural numbers. Now, it may be that the computer spits out a list of ID numbers which are supposed to receive scholarships based on grade point averages. Then we're interested in the inverse function to f, which would assign to each ID number in B the name of the corresponding student in A. So the domain of the inverse function to f is the range of f, and the range of the inverse is the domain of f. It is a great tragedy of mathematics that the universal notation for this inverse to f is f with a superscript -1, which looks just like f to the -1 power, i.e. 1 over f. We avoid confusion to some extent by writing f superscript -1 of y to represent the inverse function evaluated at a point y in the range of f, whereas to represent 1 over f of x, we would write f of x in brackets and then raise it to the power -1. Also, it is usually clear from the context which concept we're discussing. We were lucky with this student ID example because each point in the range student ID number had a single preimage back in the domain. If we had tried this with the function g that assigns to each student that student's weight in kilos at 8 a.m. on July 1st, 2007, the odds are we would not be able to identify a single preimage for a common weight, say 55 kilograms. Thus, g inverse would not exist. In this case, the inverse image of 55 is not a single student, so this inverse map is not a function. In order for g inverse to exist as a function, it would have to map each point in its domain, the weights, to a single point, student name, in the range. The difference between the functions f and g is this. F is 1-to-1, g is not. Formally, a function is 1-to-1 if distinct points in the domain have distinct images under the function. In mathematical notation, if p is different from q, then f of p is different from f of q. For ID numbers, the function is clearly 1-to-1. Different students have different ID numbers. For the function g assigning each student his or her weight in kilos, it is virtually certain that many students will have the same weight, so they will be assigned the same number in the range of the function g. So g is not likely to be 1-to-1. So our formal definition is this. If f is a 1-to-1 function, then the inverse of f exists and is written f superscript -1. And it is defined as follows. If f of x equals y, then x equals f inverse of y. We have seen how the inverse looks as a mapping. How does it look when we're dealing with the graph of f of x in the Cartesian plane? The important thing to notice is that a point with coordinates a, b lies on the graph of f of x means that b equals f of a, or equivalently, a equals f inverse of b. Thus, the graph of f contains all the information about the graph of f inverse. But now, for f inverse, the y-axis is the independent variable, which we normally call x and make horizontal, not vertical. So just to confuse matters further, we will in general write the inverse function as a function of f, and of course graph it in the usual way. In mathematics, if we are interested in the inverse of a given function f, then we try to get a formula for f inverse, and we also want to graph it, preferably using the graph of f. Here's a simple example of how we approach this. Let h of x be 3x minus 4. This function has domain R and range R. The formula tells us that given a point x in the domain, the corresponding image in the range is y equals 3x minus 4. Now you can solve this simple equation for x in terms of y. Namely, x is 1/3 the quantity y plus 4. And that is exactly the inverse function. H inverse of y is 1/3 of the quantity y plus 4. Once you have the formula for the inverse, traditionally we replace the argument y by x and write H inverse of x is 1/3 the quantity x plus 4. Here is a picture of what we've done. First, here is a graph of f. The inverse function picks a point on the y-axis which lies in the range of h, and finds the point x on the x-axis which got mapped into that given y. But then we make this all a bit complicated by making the y-axis horizontal, labeling it as the new x-axis, and then graphing h inverse as a function of the new x. This next picture shows the original function f of x equal 3x minus 4, the inverse function f inverse of x, which is 1/3 of the quantity x plus 4, and for future reference, the straight line y equals x. Now a subtle point. If the point a f of a lies on the graph of f, then the point f of a lies on the graph of f inverse. But when you interchange coordinates like this, you're just reflecting the point a f of a across the line y equals x. Look at that previous picture again and see that the graph of f inverse is just the graph of f reflected in the line y equals x. So this is an important visual tool for obtaining the graph of the inverse function. Just reflect the graph of f in the line y equals x. When we say reflect, what we mean is move the point AF of A on a line segment perpendicular to the line y equals x until the point crosses the line y equals x and has moved an equal distance from the line y equals x to the other side. You could visualize the graph of our original function h inverse of y by just considering the y-axis as your independent variable. That's a little hard on the neck because you have to rotate 90 degrees. That's why we replace y by x in the formula for h inverse. When you replace y by x in the formula for h inverse, you're putting the independent variable on the horizontal axis as we usually do. This corresponds to looking at the graph of h, which consists of points x f of x, and generating the graph of h inverse by interchanging the coordinates of all the points x f of x to new points f of x x, and this gives the graph of h inverse. Let's look at some more examples. Consider the function g of x equals x squared. This function has r as its domain and the interval 0 infinity as its range. But the function is clearly not one-to-one. Every point on the y-axis except the origin has two preimages. For example, y equals 9 has the preimages x equal 3 and x equal minus 3. Equivalently, we could use the horizontal line test. Q of x would be one-to-one if and only if every horizontal line hit the graph of Q in at most a single point. And of course, all horizontal lines above the x-axis hit it in 2 points. However, you can make the function q one-to-one by restricting its domain, and this is a standard practice in mathematics. We redefine q using the same formula, namely q of x equal x squared, but we specify the domain of q to be the interval 0 infinity. Now we get a one-to-one function. The inverse to y equals x squared is x equals the square root of y. So we can write q inverse of x as the square root of x. The domain of our original function q is the interval 0 infinity, and its range is that same interval 0 infinity. This means that the domain and range of the inverse are also that same interval. The graph of the inverse can be done from scratch, it's just y equals square root x, or you can obtain it from the graph of q by reflection in the line y equals x. As another example, consider the function p of x equal 4 times x to the 3/5 power. I've chosen that power 3/5 so that the denominator is odd, and therefore we have no trouble with domain, because you can only take even roots of positive numbers. And the numerator is odd so that the function is 1 to 1. You can see that the function is 1 to 1 by the following more precise argument. Assume that 4a to the 3/5 turns out to be equal to 4b to the 3/5. Now, you have to prove from this that a must be equal to b, and that will show the function is 1 to 1. First of all, from the equality 4a to the 3/5 equals 4b to the 3/5, you can conclude that a over b to the 3/5 is 1 by simply dividing both sides. Now, if the cube of a number is 1, then the number is 1. So a over b to the 1/5 power must be 1. But if the fifth root of a real number is 1, then the number must be 1. So finally, a over b is 1, and so a equals b. This shows the function is 1 to 1. We can determine a formula for the inverse, which I admit is intuitively obvious, by reasoning as follows. Suppose that y equals 4x to the 3/5. We want to find a formula for x given y. So we take the 5/3 power of both sides, and we conclude that y to the 5/3 is 4 to the 5/3 times x. And then we solve for x. X is equal to 4 to the minus 5/3 times y to the 5/3. And that's the formula for the inverse function. P inverse of y is 4 to the minus 5/3 times y to the 5/3. Unfortunately for all of us, it is traditional to write all functions, including inverses, as functions of the symbol x, which tends to hide the fact that our inverse function lives on the y-axis, because it is defined as the inverse of a given function y equals p of x. So, following tradition, our final step is to write p inverse of x equals 4 to the minus 5/3 x to the 5/3. We can do a similar analysis for any fractional power, but we do have to be careful to restrict the domain if the function involves an even numerator or if the denominator is even. Some quick examples without much detail. Consider q of x equal x to the 3/2 power. Then the domain must be x greater than or equal to 0. On this domain, the function is 1 to 1 and well defined, and the inverse is, of course, q inverse of y equals y to the 2/3 power. The domain of the inverse is the range of q, which is the interval 0 infinity including 0. And the range of the inverse is the domain of q, which is also that same interval. For a final example, consider r of x equal x to the 4/3 power. Then this even function is not 1 to 1. For example, r of 1 and r of minus 1 are both 1. We can restrict the domain to the interval 0 infinity, allowing 0, and then this restricted function is 1 to 1, with inverse r inverse of y is y to the 3/4 power. The domain of the inverse is the range of our restricted function r, which we can see is 0 infinity, including the point 0. And the range of the inverse is the domain of r, which is this same interval. We can also use domain restriction to define inverses for trig functions. To get started, consider f of x equals sine x, which is definitely not 1 to 1. In fact, since the function is periodic, every value of y in its range of minus 1, 1, the closed interval, has infinitely many preimages. For example, a little bit of thought shows that the preimages of y equal 1 are all multiples of pi over 2 of the form 2k plus 1 times pi over 2, k any integer. So we restrict the domain of sine x to the closed interval minus pi over 2 to pi over 2 on the x-axis. Now the function passes the horizontal line test, and we use this restricted version of the sine function, often written sine x with a capital S, to define the inverse sine function. Again, We can create the graph of the inverse sine function by reflecting the graph of sine x in the line y equals x. Notice that the domain of arcsine is the range of the sine function, namely the closed interval -1, 1. And the range of arcsine is the domain of the restricted sine function, the interval -pi over pi to pi over 2. One can use this restriction idea to create an inverse for each of the trig functions, but the only widely used inverses are the inverse of the sine and the inverse of the tangent function. Let's look at the tangent function. It is periodic with period pi and has a vertical asymptote at every odd multiple of the number pi over 2. So we restrict the tangent function to the open interval -pi over 2 to pi over 2 to get a 1-to-1 function, sometimes written tan x with a capital T. The inverse tangent function, written arctan x, is the inverse of this restricted tangent function, so it has the following graph. Notice that the vertical asymptotes for the function tan x at plus and minus pi over 2 become horizontal asymptotes for the inverse function. Finally, some basics. The composition of f and f inverse always brings you back to where you started. In terms of formulas, what I'm trying to point out is f composed with f inverse and applied to x gives you x, and f inverse of f of x equals x for any appropriate x. By appropriate, I mean that in the first case, where we claim that f of f inverse applied to x gives x, x must be in the domain of the inverse function. But in case B, where you state that f inverse of f of x equals x, x must be in the domain of f. This is important to keep in mind. For example, consider the function f of x equals square root x, with domain x greater than or equal to 0 and range the same. Then the inverse function, f inverse of x, is the square of x. But this inverse is only defined for x in the range of f. That is only defined on the interval 0 infinity. The formula x squared can be computed for any x, but that doesn't matter. The inverse function is only defined for x greater than or equal to 0. For this example, the left half of that parabola does not exist. If you carelessly write f of f inverse of x is the square root of x squared equals x without adding for x greater than or equal to 0, then you're in trouble. Because for x negative, the square root of x squared is not x, it's minus x. For example, the square root of minus 3 squared is 3. So those very useful formulas involved in the composition of f and f inverse, always giving you back x, need to be stated very carefully with domain and range of f and f inverse clearly in mind.